I'm presenting this work on behalf of Cheng, who's the PhD student who did most of this stuff. So this talk will be back down to 2D again. We're taking a look at anchor losses. So just a quick summary about what we're looking for in good resonators, be it for oscillators, filters, or resonance sensor applications. What you want in a good resonator is you want low insertion loss, you want high quality factor, and so in terms of high quality factor, that's really looking at the selectivity of that peak, and with low insertion loss, what helps to get that low insertion loss is good coupling between the interfaces. Of course, a high Q would also bring down the insertion loss as well. So we've worked quite a bit on both capacitive silicon resonators, and this is something that's well known in the MEMS resonator community. On one hand, you've got capacitive silicon resonators, and you can get up to Qs over 1 million. But where they do suffer is that you've got very low transduction efficiency. So unless you've got really, really small gaps, the insertion loss tends to be quite high. And on the other hand, you've also got piezoelectric, so in which the entire body is made of a piezoelectric, for example, like aluminum nitride. Transduction efficiency is high, so you get very low insertion losses, but the Qs are typically in the range of thousands or so. And what's been kind of pioneered by Farouk is this thin film piezoelectric on silicon, whereby you kind of combine the goodness of silicon together with the aluminum nitride, so you get low damping from the silicon, you get nice transduction efficiency from the piezoelectric, and so you get a good best of both worlds, and you get slightly higher quality factors. So you can reach up to about 100,000, depending on the thickness of silicon. So that's what a thin film piezoelectric on silicon stack looks like. You've got aluminum nitride, and it's sandwiched between an electrode and silicon at the bottom. So how do these actually work? So we're looking at these what we call contour mode resonators. So they are 2D resonators. So you stick these metal electrodes on the top, and then you've got the piezoelectric, and then you've got the silicon, so that's grounded. You put a voltage on the top electrode, and that drops a field, and through the reverse piezoelectric effect, that generates a lateral strain, and that drives the mode in the width direction. So these modes are actually kind of vibrating laterally. In this case, it's vibrating along the width. And so with TPOS, as I mentioned before, it's a combination of aluminum nitride and silicon. So you've got high coupling efficiency from the aluminum nitride, and then for the silicon, that provides low damping. And so the frequencies with these are really kind of defined by the pitch width of these electrodes out here. So when you take a look at contour mode resonators, as I said, it's defined by the lateral features, so it's vibrating in plane itself. And well, I have to emphasize that these are in-plane modes primarily. And what happens is you've got to clamp them somewhere, as we've seen in the previous talk. And so that gives you a physical connection as well as an electrical connection. And one of the losses is really coming through the anchors themselves. And this has been kind of like seen in quite a few works. And so it's people try and find ways of getting around it and increasing Q and reducing anchor loss. So for example, people have tried to shape the resonators and in order to confine the energy to the center, and that's been found to actually raise the Q. And that would be one more data point to say that anchor loss is a matter. Or, for example, putting these reflectors at the end, and these are acoustic reflectors that reflect energy back into it. Or, for example, using other kinds of novel structures like phononic crystals that creates an acoustic band gap, and that also acts to reflect the energy back, out of these tethers into the resonator itself. And so the motivation of all this work is, well, something is going on in tethers. We want to see what exactly is actually happening in the tethers. Can we actually visually see it instead of just looking at quality factors? And so there's been work done rather recently using based on aluminum nitride resonators, and they've used this laser Doppler vibrometry to basically profile the surface as the resonator is actually vibrating. And what they've done is they've actually seen that there are actually these waves that actually go on down here. So something is going on. And so a closer look at TPOS resonators, I mean, although the mode is generally lateral, I mean, if you actually do an FE analysis of it, you do see that there are these kind of waves that go in the out of plane direction. So, well, what happens with this is because now instead of having a pure aluminum nitride, now you've also got this heterogeneous stack of materials, and so this mismatch, this difference in the elastic properties would generate more out of plane bending. So we thought, okay, why not actually use this kind of method to actually see what's actually going on. So the way that we thought we'd do it is actually take two resonators, which we know have very different Qs and should give very different profiles. And so can we actually see these differences in the profiles on the vibrometer itself? And so differences in Qs, that's just a normal resonator with a very flat edge. That's another one that's got a curved surface. And what that does, as we've seen just now, is actually concentrates the energy in the center. And the difference is quite stark. It's on the average about, as much as a factor of 6. And this has been measured over several devices, so it's quite consistent. And our aim was actually to provide some large contrast that correlates the visualizations from vibrometry to the differences that we see in measuring the quality factor. And so we can do some of this FE analysis just to show and see what happens that you do get this kind of concentration in the center, and that helps to raise the quality factor. But if you actually do a scan on the z-axis, you do see this kind of wave that I saw just now, and when you actually bend and you curve these sides, you actually see this concentration, so it moves the waves away from the edges down to here. So this can be seen from FE, and we take a look at what's happening down here. This bending over here is actually the beam bending up and down. So sometimes people say that the waves are coming out of that, but well, there is actually quite a bit of bending. So could we actually see these effects? And just a little bit of a illustration of what we mean by difference. So these resonators, the one with a biconvex, a curved edge, that's got a Q of about 12,000 or so, and these are 10 micron thick silicon resonators. And for the other one, that's a conventional flat edge, that's got about average Q of about 2,000 or so. So quite stark differences, so everything kind of lines up in terms of all the properties. So if we do a scan of with the vibrometer, you do exactly see that kind of a ridge over here. You get these peaks over here, and that corresponds to where the nodes are. Do a scan along the supports themselves, you also see this kind of a wave. And what is interesting is that the amount of displacement you see down here and the amount of displacement you get right over here is pretty much comparable as well. And then now we do a scan on the one with the curved edge, and we do see now there's a difference because it's concentrated right in the center. And when we actually scan that surface over there, you see that's about 2.6 picometers. It's a huge difference compared to what's actually being concentrated at the center. And so just to kind of like summarize and put everything, that's what we kind of simulate in FE. That's what you measure in the vibrometer measurements. And you kind of see it's almost like a copycat of each other. You see these ridges down here. You also see these ridges down here. You see your concentrations in the middle, see your concentrations. And just to kind of summarize all of this data up together, in terms of the amount of displacements you're seeing, it's pretty much comparable to what we're seeing in the FE analysis. So this method does seem to be able to map out what we see in FE. Until this point of time, there's no way of actually experimentally verifying that if these FE simulations are indeed true. So in conclusion, these vibrometry measurements reveal out-of-plane displacements in the TPOS, these CMRs, and these measurements can actually map out, as I've shown, these vibration profiles that match the FE analysis. And these visualizations actually, they indicate some correlation between the amount of bending displacements in the deformation in the tether supports and the measured quality factor. So at this point, I would like to just acknowledge funding from the Research Grants Council of Hong Kong, and also this joint research scheme as well. So that, I think I'll be happy to take any questions.